This is Unit 13, Properties of Solutions, Lesson 13.2. I found in this project that this was a little too big for just one video, so I've decided to break this up into two videos. First, there will be Heat of Vaporization, and this will be video 13.2. And then the second part of this project will be Solids, and that will be video 13.3. So let's talk about the heat of vaporization. Basically what we're talking about is the energy it takes to change a liquid into a gas, or the reverse, the energy that must be removed to turn a gas into a liquid. By definition, the heat of vaporization is per mole, or it could be per gram. Either way, this is a constant for each substance. And let's take a look at the magnitude and compare that to the strength of the intermolecular forces involved. I will begin with the bottom of the three substances and work my way up. So perhaps you'd like to watch the entire presentation before you actually write your notes. First, let's consider chlorine gas. Chlorine gas is held together by London dispersion forces. Remember, these are the weakest of the three intermolecular forces. We find that the enthalpy or heat of vaporization is 10 kilojoules per mole. Next, there's hydrogen sulfide. Hydrogen sulfide is a polar molecule, and you have dipole-dipole forces, and you can see that the heat of vaporization is almost double. Last, we'll consider water. Water has hydrogen bonding. This is the strongest of the three intermolecular forces. So we shouldn't be surprised to see that the enthalpy of vaporization is over 4 times greater for water with hydrogen bonding than it is for chlorine gas with London dispersion forces. What this demonstrates is that as the intermolecular forces increase, so does the enthalpy of vaporization. So polar molecules will have higher heat of vaporization than nonpolar molecules if they are similar size. Because remember, dispersion forces increase with molar mass. So when we say similar size, we want to make sure that the molecular weight is not a factor. Also remember that converting a liquid into a gas is an endothermic process because energy must be absorbed. So if I wrote this into an equation, I would make sure that heat is on the reactant side. The two ways that you'll see enthalpy of vaporization on your AP exam will be with conceptual questions, but you'll also see it mathematically in the problem I'm about to give you. Let's go ahead and take a look at a similar problem to what we did in honors chemistry. If you'll recall, in honors chemistry, we talked about the heat of fusion, which was turning a solid into a liquid. And at that time, we wanted to know how much energy it took to turn some ice into water at the boiling point. Now let's do the other half of this. Let's start with 47 milliliters of water at 35 degrees Celsius, and I'm going to raise it to 100 degrees Celsius where it starts to boil and then convert it into steam. We'll do this in two steps. First, I want to calculate the energy needed to raise the water temperature from 35 to 100 degrees. In order to do that, I need a constant, and that constant is going to be the specific heat capacity of water, 4.18 joules per gram degree Celsius. This is what we need to change the temperature. Also, I'd like to point out, remember the density of water is 1 gram per milliliter at most room temperatures. Therefore, when a problem gives you 47 milliliters, we can simply change that into 47 grams. This will be the equation, and you'll be given this equation on your AP exam sheet, and this will be Q is heat equals specific heat capacity times the mass of the solution of the sample times the change in the temperature. The next step will be to calculate the energy needed to change the water into steam. In order to do this, we need to use our constant. For water, it'll be 43.9 kilojoules per mole. Now notice some conversions are going to be necessary here. Don't forget, this is in joules, this is in kilojoules. Also, this is in grams, this is in moles. The third step will be just to add these two together. Now let's begin with step 1. This is just plug and chug. We're going to take our equation, put in the specific heat capacity for water, times 47 grams, and the temperature change is a positive 65 degrees. Remember, it's always the final temperature minus the initial temperature. So when it's endothermic, or the temperature is being raised, then it's a positive value, and we get 12,769.9. And because it's 3 sig figs, this would be 12,800 joules, which I've converted to kilojoules, so it will match the heat of vaporization. With step 2, we've brought the water up to 100 degrees. Now we need to change the water into steam. So this mass, 47 grams, has to be changed into moles. There's the molar mass of water, 18.02, and then we multiply that times 43.9. Just follow the units. Grams cancel, moles cancel. That gives us 114.5 kilojoules. Because this is 3 sig figs, I rounded to 3. And now it's just a matter of adding these two together. And my final answer will be 128 kilojoules. And that's the end of video 13.2. And go ahead and proceed to video 13.3 and watch solids. Then after 13.3, you can go to Moodle and answer the questions, which will cover both videos.